All right, here we go. Now I will screen share. Just make sure that this is fully in there.
All right, I'm gonna have to grab all the pieces of this. Just give me a moment here to get to where I can do that.
This should be the whole page.
All right, I think I have enough to for us to get started here. Do we need to go through 6 and 7 again, or is that solid for you?
6, 7, and 8 are all good.
Oh, good. Okay.
Eight
So up
for
to-
8. For 8 was we said always decreasing and concave up because first derivative is negative and the second is decreasing.
Second derivative is the first derivative is always negative.
Mhm.
So let me share that because I think maybe that was we were rushing towards the end of this. Let me start there.
Sure.
I'll share my screen and hopefully get this cleared. So the first derivative p prime of h is did you end up multiplying these numbers?
Yeah.
If not, what did you get for that?
It's like for the first one, it's like negative 9.69 times 10 to the negative fourth, and e to the whatever.
So I'm just gonna call that k for the moment. K times h, and then p double prime of h was positive something. What was?
It's positive 3.27 times 10 to the negative 17th, and then e to the negative,
Okay, so what the answer for the answer for 8 has to say is that p prime of h is less than 0. And less than 0 means negative, but that's another way of saying it. And that implies that it is decreasing.
Oh, okay.
That's why it's decreasing, because the first derivative is negative. And so that's what they're looking for. I mean, your instructor is grading you based on like having those words there. Now, p double prime of h is greater than 0 or positive. And that implies second derivative is about concavity, that it's concave up. So a function that is decreasing and concave up looks like that.
Oh, okay.
Decreasing because it's going down and to the right. The tangent lines are going down and to the right.
Yeah, concave, yeah, because down to the right. It looks like a little spoon.
Yes. Okay, so now we're gonna graph this function. Okay. And the interesting thing here is the domains are different. Why does, like, see how this is 30,000 here, it's 3,000. I don't know. We'll deal with that moment. But I'm gonna go to Desmos because it's a way better graphing tool than your calculator.
No argument for me.
Yeah. So p of h just means y, and instead of h, we're going to use this x. So we're gonna go minus 3.23 times 10 to the minus 5, and then x. So still got an x, and you notice like there's nothing graphed. Okay.
Yeah.
You go to this graph settings. It's very intuitive here. The x is going from 0 to, and that's where I didn't know. There's 3,000. I guess look up to 30,000. The y is where it's like, hey, what do we do there? Well, I'm going to just increase it until we see something. See, I went too far. Now we can finally see something here. So let me go to 50. So let me do this at, I don't know, 35. I still don't like that. Let me see if I can change this. No, we got to go 30,000. Okay. All right. So what you're looking at here is what you have to now put on your graph. And I'll snip in this and I'll also draw it on the page, but it needs to like be somewhat reasonable. Like it has to, like I call it the eye test. Like you need to make your instructor believe that you know how to graph this thing. And like there's things that are giveaways, like, hey, he doesn't have any idea. But if we say, okay, if we just say like, for example, that this is 30, and this is 30,000, like it's gonna do something like that. You know, that's kind of believable for you. Now, I don't know how many points you got to graph and so on, but like, I think that would be considered good enough.
Okay. All right, I'll just draw that down real quick. Let's see if I can get it. What's this? That's weird. So on the graph, it's only 25 to 30, so it would be a little bit
What do you mean on this axis?
yeah, on the y-axis it only goes from 25 to 30.
Says who? Says
The little graph thing.
on your paper?
Yeah, on my paper from 25 to 30 on the y-axis.
Okay, well then I can change this on my side and I'll snip in a new one, but it's
I think that's pretty bizarre that it would do that.
it looks like a straight line when you do that. I don't know, it's really weird. So let me change it to 3,000. Maybe that actually does work. See, this is one of those things where the instructor they probably, oh yeah, I'm going to change that, and they never do. So but yeah, there it is. Okay, well, it does kind of look like a straight line. It actually looks more like a straight line.
Yeah, and then you look at 30,000, and then you look at 30,000, it's completely the opposite.
Yeah. So I don't know what to tell you on that. I mean, that's like a question. Sometimes they post in the announcements that you know, hey, there was a correction for this.
Yeah, like take a look at this because this is all screwed up.
All right, I did not get any snips past 9. So if you want to
share again.
share your screen, we can look at that part together.
Sounds good to me. Hold on. Share, and then here. That should be it.
There was the second page there. I think we.
Oh yeah, this is the second page that we just got.
Yeah,
This is the page that we didn't get.
We didn't. 10 and 11. We haven't gone through unless.
Oh, okay.
Oh no, I see what you're saying. We didn't do that last part though.
Okay.
So if you want us to do it.
Yes, please.
Okay, so like what I sent you for, so just to be clear, the graph that I made is okay. If you're, when I share my screen again, the graph that you just saw, let me share my screen, is for part 9. Let me share my screen. Sorry, there it is. Go share screen. Okay, this is correct for number 9. This is totally correct for part 9. Part 10 is different. Part 10 is where you actually have to make a different window. And I don't know if that was made clear. Like this to me is correct for 9 because it's this graph here.
Yeah.
But for 10, they're saying, okay, now here's a different window. Oh, it's both the climber's function and the physics function. So they want you to graph both of these things. So you have to, we can't do this until we do part A or part 1 through whatever. So I guess you do have to go back and share that. We have to come back to this.
I'll share real quick.
All right, let me grab. right, so I'll try and grab them all this time, and then I won't have to go back and forth.
I'll be right back.
Sure. All right, so we're going to go back and look at this. It says higher altitudes can present a challenge to mountain climbers and hikers. One of those challenges is dealing with air pressure changes. So rule of thumb is that air pressure drops about 1 inch for every 1,000 foot increase in height above sea level.
All right.
Okay, so this is the slope, by the way. This is the slope. So they're saying at sea level, the air pressure is 30 inches of mercury. So like graphically, it's 30 and it's going down like this. And the slope of this line is 1 over 1,000 feet.
Okay.
So
Understandable.
I'm sorry.
I was just saying understandable.
Yeah. And so they want you to write this function. So the function is C of H equals 30 minus 1 over 1,000 times H.
Oh, that's it.
Yeah, now there's a bit that goes into that, but let me just actually double check that this is actually reasonable on our graph here. Yeah, that is reasonable.
Yeah, because it's like going so slowly down that you have to get to like 30,000 before you see that it's actually curved up.
Yes. Yeah. So it's a pretty good approximation for a while. And I think that's the whole point of this here. So the summit of Baba Dog Mount Lemon north of Tucson is roughly 9,200 feet above sea level.
Okay.
Okay. So the thing that isn't maybe clear here is that H is in thousands of feet. So when it says 9,200 feet, that's an H of 9.2.
Oh. Oh, okay. So it tries to trick you a little bit.
Yeah. And I think that's why the units are different or different there. So why does that matter? Well, you're doing C of 9.2, 30 minus 1 over 1,000 times 9.2. But I said that there, but then this wouldn't be right. Maybe it is. All right, I'm gonna go search the internet and find out what the actual pressure is on Mount Lemon, so we can get a
Feel for it, I guess.
see if which answer is reasonable here. So yeah, so this actually is the reasonable one. So this is confusing. It's a units issue, but you throw this in your calculator and you get 30 minus 1 over 1,000 times 9.2, and you get 29.991. And that is reasonable-ish. If you look at a weather forecaster, it's like 29.98 there right now.
Are there any units that we put here?
Yes, the pressure is inches of mercury. And so it's 29.91 inches of mercury. And believe it or not, that there's actually these like measuring devices that actually have that much mercury in it.
Oh,
It will truly go up and down based on factors.
that's weird. Never heard of that.
Yeah. Okay, so did you get that down for number 2?
Yep, just got that written
Great.
down.
Great. So number 3 is the same question, except you're converting 14,500
Mhm.
and you have to divide by 1,000. Okay, and the reason is it's got to be in the right units of H. So H in this case equals 14.5.
All right.
And that doesn't seem like it's going to be a great thing here. Let me look at that also. I'm still not convinced. All right, so the way this works is it's C of 14.5, which really isn't that different. So it's going to be 30 minus 1 over 1,000 times 14.5.
Alrighty.
Which really isn't that much different than what we just did. It's going to be pretty insignificant. It's going to be 29.99. 29.985 inches of mercury. I really don't like that.
Inches of mercury. All right.
So I want to look at the graph again. This is really an odd question. Yeah. See, I don't think we're doing it right. Sorry, it just the way this instructor's doing this, it's 1 inch for every 1,000 foot increase. So you have to, it's H's in thousands of feet. So if you put in 9,200 feet, yeah, I tend to think we haven't done this right. I tend to think that this should be 9,200 here. And it gives a slightly better answer, especially for the next one, for that Mount Whitney. So let's do this again, because I just don't think you're going to get an answer that's reasonable here. So this would equal 20.8.
Okay.
And it's inches of mercury still.
200.
And then
That first one was 20 point what?
20.8.
3.8 inches mercury. All right, got it.
And then the next one here, we'll do it for 14,500. So that's 14,500.
Mhm.
And then that changes this substantial. It's going to be 15.5. So apologize for that. I think it'll
Oh, that'll be fine.
clear it up. So then the last part here is like, okay, where is C of H, which is 30 minus 1 over 1,000 H? Where does this equal 0? So you're solving for H. Okay, so you got to show your work here, and let's you're solving for H. So 30 equals 1 over 1,000 H. H equals 30 times 1,000, which is 30,000 feet. That's the show your work part because
Looks good to me.
Yeah. Okay, now number 5, it says to find the derivative of the hiker's estimate function. So your estimate function is this 30 minus 1 over 1000 h.
Mhm.
Okay, and so the derivative of this c prime of h, the derivative of 30 is 0. Dx of a constant times x is always the constant. So the derivative of this is just the constant. So it's minus 1 over 1000, like that.
All right.
Now we have to explain. We'll do that in a moment. Let me know when you get caught up here.
Okay. I'm caught up.
Okay, so like, why does this make sense? Well, if you go back to like the original sentences, it says it decreases. That's the negative, decreases by 1 inch for every 1000 feet. So in context here, excuse me, the decreases is from this negative. This 1 is this one right here. This 1000 is this 1000 here.
Okay. What should I write on the paper for explaining the work?
I'm not sure. It's got to, I'm not sure how you want to phrase it, but you're basically trying to say the slope, the derivative is the slope. The slope is decreases 1 inch for every 1000 feet. So I'll try typing that. The derivative is the slope. The slope is minus 1 over 1000, or a decrease of 1 inch of mercury for every 1000 feet of height increased, something like that.
All right, I finished writing it down.
Okay, so
On the 10 and 11.
yeah, if we go to this last one, and I'm going to snip it and go down. So what they want you to do is graph the two. Oops, why did that snip there? They want you to graph both of them in this window from 0 to 5000 and 25 to 30. So let me snip that in our window here. So 0 to 5000, and y is 25 to 30. Yeah, all right. So I'm going to snip this and then I'll graph it in there. But what you're going to see is they're basically close enough that like you would say that's pretty good as an estimate. Let me resize this. Never scales well. There it is. Okay, so basically what they're saying is like that one, the red one is the second page, the blue one's the first page. They're like pretty good for a while. Okay, so like you have to use colors. I don't know. You want to you want to basically show that like one is good, one goes straight down. Oops, one goes straight down, and then the other, which is blue, it's a little above. And the colors don't really matter, but it's like, yeah, there's a gap.
Oh, okay.
That's what this picture is trying to show here, is that like they start separating.
And then the other one goes like just a little bit of a gap. Okay.
A little bit of gap. So that's kind of what they're looking for here. 11 it says, based on your graph, for what altitudes would you suggest that the rule of thumb is sufficient to estimate pressure? Basically, like, when is the gap too big? And like the real answer to this, Jack, and this is probably the most important thing I'll say tonight. The real answer is it matters when the pressure actually can affect your body or hurt you. And we don't know that, but it's like I don't know, it's never more than one apart. Like the biggest gap is down here, and that's 0.5 inches of mercury.
Mhm.
And I don't know if that's important or not, because I don't know anything about air pressure because I live on the ground. But like to me, it's a pretty good estimate everywhere. But your instructor might think, well, I don't know, where do you think it's substantial? And maybe saying like from 0 to 3,000, it's pretty good. But people literally hike 14,000. I'm sorry, 14,000 high mountains.
That's a lot. That's a lot.
Yeah, you see that they'll put on the 14K club or the 12K club. Yeah, but the thing is, they're already starting pretty high, so it's a little, it's not necessarily the same. But I don't really know how to answer this last one other than to say, like, you could just say, well, it's spreading apart the whole time, but maybe after 3,000, it's more substantial.
Around 3,000, it's more substantial.
And that's just Matthew's opinion. It really 3,000 feet. That's my opinion. I couldn't tell you like for sure, because what really matters is when does the pressure actually impact you, and it's different for everyone. There's actually such a thing as what do they call it? You get when people go up in elevation, they get sick. Like the people who drive to Santa Fe, they call it altitude sickness. And
Yeah.
I don't know what it's like because I've never experienced it, but to them this would matter. And I don't know at what point it matters for that.
Yeah, that is true. Because everybody's a little bit different.
Yeah. So if you get something down and you kind of back it up, you'll probably be fine.
Can we go back to like the graph for number 9 so I could draw that down again?
Yes. So the graph for 9, this is the one I would use, something that looks like this. It's really the right window there.
That's like around, okay, so 30, 30, 30. 20. I just have to draw the little lines right over. So that looks like, okay, then I run 10. That's about right. All right, that's everything I wanted to do. Thank you for your help.
All right.
Matthew.
Thanks so much, Jack. I'll see you next time.
See you tomorrow at 8.
Okay.
Thank
Great
you.
night.
Bye-bye.
Bye.